Usually when you step into a hot shower, you don't really think about the sheer amount of raw energy required to instantly heat that water.
Oh, absolutely not.
You just turn the handle, the water gets hot, and that's it. We treat it like this basic utility, right? Like a clean binary. It's either cold or it's hot.
Yeah, I mean, it is the ultimate modern convenience. You just expect it to be there, waiting under pressure in the pipes, ready the literal second you need it.
But when you actually peek behind the curtain of autonomous heat supply engineering, suddenly that hot water isn't just a simple utility anymore.
Not at all.
It turns out giving you a hot shower requires this incredibly precise, almost beautiful mathematical translation of literal sunshine.
It really is the absolute definition of engineering elegance. You know, you are taking the raw, unfiltered chaos of a star millions of miles away.
Right.
And through applied physics, turning it into predictable, measurable human comfort inside a bathroom.
Which brings us to today's deep dive.
Yeah.
Welcome. If you're listening right now, maybe you're an engineer prepping for a massive project. Or maybe you're just like us, someone who wants to understand how the hidden gears of the world actually turn.
Exactly.
Today, we are cracking open a deeply technical engineering text. It's simply called a 5-dot PDF, and it's entirely dedicated to calculating solar systems for building heat supply.
It sounds dry, but it is fascinating.
It really is. Our mission today, to uncover the secret math behind how engineers capture raw sunlight and translate it into a warm house, a hot shower. We're going to decode the entire journey, from a single photon of sunlight hitting a roof all the way to $1 saved on your monthly energy bill.
And to start that journey, we have to look at the fuel source. Before any engineer can even begin to design a heating system for a house, they have to know exactly how much quote-unquote fuel they are getting from the sky.
Right.
They have to mathematically capture the sun.
Which honestly sounds impossible. Like if I want to know how much gas is in my car, I look at a gauge. But how do you measure sunshine? It's not like you're pouring sunlight into a bucket.
Well, it requires looking at the environment in a highly structured way. The baseline is actually pretty simple. Engineers look at the total solar energy hitting a perfectly flat horizontal piece of ground.
Okay.
You can pull that raw data from any local climate directory. But a flat piece of ground isn't a solar collector.
Obviously.
Right, so to figure out what actually hits a tilted solar panel on a roof, they use what the text calls Formula 5.1.
Okay.
They take that baseline flat energy, denoted as E, and multiply it by a specific conversion coefficient, which is R, to get the energy for the tilted collector.
Okay, wait. I understand tilting a panel towards the sun makes it work better, but what if I live somewhere that gets terrible winters with just a ton of cloudy days? Shouldn't I just give up on solar?
Yeah.
If there's no direct sun hitting that panel, there's no energy.
Yeah. See, that is a very common misconception, and it's exactly why that conversion coefficient, the R in the formula, is so crucial.
How so?
It corrects for that exact assumption. The underlying math, specifically Formula 5.2, shows that this coefficient isn't just a single flat number. It represents the physical reality of how light behaves in our atmosphere.
Okay, so it's broken down.
Yeah, it's actually split into 3 distinct components to account for the specific angle of your roof. You have direct solar radiation, sure, but you also have diffuse radiation and reflected radiation.
So if I'm thinking about this like a photographer trying to light a subject in a studio, you've got your main flash, that's the direct radiation, the sun hitting the panel straight on.
Exactly. On a clear summer day at noon, that direct flash is doing the heavy lifting.
But then you have a softbox. Even on a totally overcast day, light is scattering through the clouds in the atmosphere. Otherwise, it would be pitch black outside.
Right.
So that scattered light is your diffuse radiation. The panel's still picking that up, even if you can't see the sun itself.
It is. And finally, you have your bounce card on the floor. That is the light hitting the earth, bouncing off the ground, and reflecting back up onto the panel.
And this is the part that totally surprised me in the text. To calculate that bounce, engineers use a variable called the albedo coefficient.
Yes, the rho symbol.
Right, it measures the reflectivity of the ground. And what's brilliant about how engineers calculate this is that they factor in the environment itself. The albedo coefficient changes drastically depending on the season.
Oh, massively.
Yeah, like in the summer, the albedo is usually around 0.2, but in the winter, it jumps all the way up to 0.7.
And if you think about what happens in winter, it makes perfect sense.
Snow.
Snow. Snow is highly reflective. So what's fascinating here is that, ironically, in the dead of winter, when the days are shorter and the direct sun is much weaker, the snow on the ground acts as a giant secondary solar panel. It's literally bouncing sunlight directly up into your tilted collector.
Wait, so the environment itself becomes part of the machine. The snow is actually helping heat the water.
Precisely. The landscape is actively participating in the thermal exchange.
Which proves this absolutely isn't a set-it-and-forget-it technology.
Right.
If you look at the raw data for these tilt coefficients in Table 5.2, the optimal math shifts every single month.
It has to.
To get maximum efficiency, engineers have to account for exactly where the Earth is in its orbit around the sun and what the ground looks like below.
And crucially, it depends entirely on where you live. The global context here is pretty stark.
Yeah.
If you look at the annual average solar radiation on a horizontal surface up near 68 degrees north latitude, you might only get 800 kilowatt hours per square meter.
Wow, that's low.
But if you drop down to 39 degrees north, you're getting a massive 2,000 kilowatt hours.
Let's ground this with a concrete example from the source material. They used the city of Kiev, which sits at a latitude of 50.5 degrees.
Right.
If you just lay a 1-meter square box flat on the ground in Kiev over the course of a year, it receives 1,220.3 kilowatt hours of solar energy.
That's our baseline.
But if you take that same box, turn it into a solar collector, and tilt it at a 45-degree angle facing south.
You apply that conversion coefficient we were just talking about. For Kiev, at that specific 45-degree tilt, the average annual multiplier is 1.09.
So you take that baseline of roughly 1220 multiplied by 1.09, and suddenly you are capturing 1,330 kilowatt hours per square meter every single year.
Exactly.
You didn't buy a better panel. You didn't invent new technology. Just by knowing your geometry and angling it to catch the direct rays, the diffuse sky, and the bouncing snow, you've captured nearly 10% more raw energy.
It's pure physics working in your favor. But you've only solved half the problem here.
No.
This is just the supply side. You've successfully caught the sun. Now, how do you translate that to human comfort?
Yeah, because we figured out how much sun hits the roof.
Yeah.
But how do we connect that 1,330 kilowatt hours to the actual shower head? Capturing the energy is great, but my shower still needs to be hot.
Well, to do that, engineers have to calculate the sheer physical resistance of water.
Yeah,
When you transition from the sky to human needs, you introduce some unyielding constants of nature. Chief among them is the specific heat capacity of water, which is 4,190 joules per kilogram per degree Celsius.
that is a very dense, specific number. What does 4,190 joules actually mean in the real world?
It's basically a measure of water's stubbornness.
Stubbornness, I like that.
Water is incredibly resistant to changing its temperature. Like if you put a metal pan on the stove, it gets screaming hot in seconds. Metal has a low heat capacity,
Right.
but water takes its time. It takes exactly 400 and 190 joules of energy to force just 1 single kilogram of water, which, given water's density of 1 kilogram per liter, is exactly 1 liter to rise by just 1 degree Celsius. It is a massive energy sink.
So engineers have to fight the fundamental stubbornness of water, and then on top of that, they have to factor in human behavior. Which brings us to Formula 5.3 in the text.
Yes, the hot water energy needs calculation.
Because how many liters of water you use dictates how many times they have to apply those 4,190 joules. And this is where human unpredictability creates just wild variations in the math.
Oh, absolutely. The engineering models in the text compare different household scenarios using a nomogram, figure 5.1, and the difference is staggering.
Let's look at the family of 5 they mention.
Okay, so this family, they like their hot water. Maybe they take long showers, run the dishwasher constantly. They're using an average of 75 liters of hot water per person every single day.
Okay, so a family of 5 using 75 liters a day. The text shows that over a year, to fight the stubbornness of all that water, they require a massive 8,600 kilowatt hours of energy.
Yes.
They're heating 125 cubic meters of water a year. If you're listening, imagine a large swimming pool. That's basically how much water they are boiling.
It's a huge amount. But then contrast that with the second example, a family of 4, and they are just a bit more conservative.
Right.
They take normal showers. Maybe they use cold water for their laundry. They only use 50 liters of hot water per person per day.
And according to the nomogram, that family only needs 5,600 kilowatt hours a year, heating just 65 cubic meters of water.
Exactly.
That is a massive drop in energy demand. Just by having one less person and taking slightly shorter showers, their energy footprint is nearly cut in half.
It really highlights the human element in the engineering.
But wait, as I was looking at Formula 5.3, the actual equation they used to calculate this total energy load, I noticed a really mysterious number sitting right at the front of the formula.
Ah, the 1.2 multiplier.
Yes, The math literally dictates that the total energy needed equals 1.2 times all the other variables combined. Why is there an automatic 20% tax on this calculation? Is it like over-ordering pizza for a party?
That's actually a great way to put it.
You do the exact math, 3 slices per person, 10 people, 30 slices, but you always buy a few extra just in case someone brings a friend or drops a slice on the floor, some mathematical buffer, or like a long shower tax.
The pizza analogy is perfect because engineering must always account for a fundamentally imperfect world. That 1.2 is a built-in safety margin for heat loss.
Right, so if you're listening right now and wondering why the hot water in your upstairs bathroom takes 30 seconds to warm up, this 1.2 multiplier is exactly why. Engineers are literally doing the math on the heat your house's internal plumbing is stealing.
Exactly. Think about the journey of that hot water. You heat it in the basement, but then that water has to travel through 20 or 30 feet of copper or PEX piping inside your walls.
And those pipes are cold.
Very cold. They instantly absorb some of the heat from the water. Then the environment around the pipes absorbs heat from the pipes. If an engineer designs a system that mathematically provides exactly 100% of the heat needed for the shower itself,
by the time the water actually reaches the second floor shower head, it will be completely lukewarm.
Exactly. That 20% tax ensures your shower is actually hot when you step into it.
All right, so we've calculated the sun shining down, and we've calculated the humans taking their showers and the pipes stealing the heat. But there is a glaring chronological problem here.
The timing.
Yeah. The sun shines at noon. I usually want a hot shower at 8 o'clock at night or at 6 in the morning when it's pitch black outside.
They have a fundamental mismatch in timing. You have to bridge the temporal gap between the supply of the energy and the demand for the energy.
Which means we can't just hook a solar panel straight to a shower head. We need the hardware.
Right.
The collector panels on the roof and the accumulator tank in the basement.
Exactly. And to size that hardware, the text uses Formula 5.4 to calculate the collector's specific power.
Okay.
Engineers have to factor in the effective aperture area of the panels that actually catches the light, the optical efficiency of the glass, the unavoidable heat lost back into the outside air, and the mass flow rate of the liquid coolant constantly running through the panel.
It sounds like an intense physical balancing act. But from a practical standpoint, for a homeowner, a solar installation is generally designed as a support system, right? Like usually keep a primary gas or electric boiler, and the solar system just steps in to help.
Usually, yes. But under the right conditions, it can handle the hot water entirely. And this introduces a crucial engineering variable from the text, the F parameter.
The degree of substitution.
Yes.
Yeah.
This is the exact percentage of your total heating or hot water load that the solar system takes over from your traditional expensive boiler.
Right. Because if you want your solar panels to provide your hot water year-round, even through the dead of winter with short days, that F parameter might only be between 0.3 and 0.7.
Meaning solar provides 30 to 70% of your hot water, and your gas boiler still has to turn on to do the rest.
But if you look at it seasonally, say just operating from April to September when the sun is highly available, that F parameter can equal 1.
Exactly. Complete 100% substitution. You can turn your gas boiler off entirely. The sun does all the work.
Let's go back to our family of 5 to see what this hardware actually looks like. The ones using 75 liters a day. Let's say they live in a region getting around 1,370 kilowatt hours per square meter annually.
Okay.
If they want to run this system seasonally, turning off their boiler from spring to fall, meaning F equals 1.
To achieve that specific goal, the engineering math dictates they need an accumulator tank with a volume of 510 liters in their basement and an effective collector area of about 5 square meters on their roof.
510 liters is a massive tank.
Yeah.
I picture it like a thermal savings account.
Yeah.
You are making these rapid, intense deposits of the sun's wealth during the daytime hours, aggressively storing it up in that 510-liter vault in the basement.
Right.
And then you make a slow, drawn-out withdrawal when you turn on the faucet to wash your hands or when the dishwasher runs at night.
If we connect this to the bigger picture, that savings account analogy highlights a fundamental distinction in how we use thermal energy. Well, heating domestic hot water for showers and sinks requires daily charging and discharging cycles. You fill the thermal bank during the day, you empty the thermal bank at night. It's a 24-hour loop.
Okay, that makes sense.
But if you try to use that same solar system to heat the entire house, like the radiators, the floorboards, the cycles change entirely. You aren't just bridging the hours between noon and midnight anymore. You are trying to bridge long, multi-day periods of cloudy, freezing weather.
Oh, wow. which requires an entirely different scale of storage. A 510-liter tank will get you through the night, but it definitely won't keep your house warm through a 3-day blizzard.
Exactly.
So we built this system mathematically. We have our 5 square meters of panels and our 510-liter tank. But from an engineering standpoint, if this system costs more to run than a standard gas boiler, it's a failure.
Usually. Yeah.
How do they prove this is actually worth the money? Let's talk economics.
Ultimately, engineering serves humanity, and part of that service is financial viability. You have to prove the return on investment. So the text provides Formula 5.5 to calculate the financial efficiency of the system in local currency.
And this is where it gets really interesting. The equation is remarkably simple once you've suffered through all the hard physics.
It really is.
The financial return is essentially the cost of your alternative energy, the exact price per kilowatt hour of whatever grid electricity or fossil fuel you normally buy, multiplied by the total solar energy produced by your new system, which is QNNS.
Right.
It takes the vast, chaotic nuclear fusion power of a star, runs it through panels and tanks and heat loss coefficients, and elegantly reduces it to a simple currency exchange.
And finding that total solar energy produced, Formula 5.6, means looking at the whole picture. The total energy is a combination of two distinct things: the heating energy you substituted for the house, plus the hot water energy you substituted for the showers.
Let's look at one final fascinating example of this in practice from the text. Imagine a house with a massive annual heating need, say 26,000 kilowatt hours a year just to keep the ambient temperature of the rooms warm.
That is a very significant load. You are fighting the winter cold constantly.
Very significant. And if you run the numbers on that house using the nomogram in figure 5.2, trying to achieve an F parameter of 0.7 for that heating load, meaning you want solar to support 70% of the radiators, you actually end up meeting that exact same 510-liter accumulator tank we talked about earlier.
This raises an important question about how we define true efficiency in engineering.
What do you mean?
Efficiency isn't just about the maximum raw energy you can blindly capture from the sky. It's about the exact financial offset of whatever expensive fuel you're replacing.
Right.
A 510-liter tank supporting a massive 26,000 kilowatt-hour heating load is operating completely differently than a 510-liter tank providing 100% of a summer shower load.
Okay.
One is doing heavy, continuous lifting alongside a boiler, while the other is acting as a standalone daily battery. But the math and the financial equations, they bring it all into a unified perspective. It proves the monetary value of both setups.
It's incredible to step back and look at what we've covered today. What seems like a dry engineering document full of Greek letters and complex thermodynamics is actually this practical treasure map.
It really is.
It gives us the precise instructions to capture invisible radiation, bounce it off the winter snow, fight the stubbornness of water, store it in a massive thermal bank in the basement, and turn it into real, tangible financial savings. It transforms the sun from a generic star in the sky into a localized, predictable utility.
It reminds us that modern comfort isn't magic. It is constructed. It's carefully, meticulously calculated.
But as we wrap up, I want to leave you with a final thought to ponder. Something that isn't explicitly written in these equations, but shadows every single one of them. Well, all of these formulas, the optimal tilt coefficient, the average monthly solar radiation, the expected albedo winter snow, they all rely heavily on historical climate data.
Right. They rely on the weather behaving the way it always has.
Exactly.
Yeah.
But as our global climate becomes more erratic and extreme weather events become the norm, will these static engineering formulas need to become dynamic algorithms?
That's a huge issue.
If the winter snow doesn't fall, you lose your 0.7 albedo bounds. If the winters get harsher and less predictable, will our 20% pizza buffer, that 1.2 heat loss multiplier, need to double just to keep our houses warm? The math is perfect, but the world it measures is rapidly changing.
It is a vital question for the entire field. I mean, the physics of water won't change, but the environment around it is. Engineering will have to adapt just as quickly as the climate does to keep that hot water flowing.
Thank you for taking this deep dive with us today. Hopefully the next time you step into a hot shower or, even just look up at the sun on your commute, you won't just see a basic utility or a bright light. You'll see a massive, calculable energy source, engaging in an intricate dance with the earth, just waiting to be harnessed. Until next time.